Hello everyone. In today's session, we are going to discuss about post-correspondence problem. Post-correspondence problem is a normal puzzle problem where you'll be having two set of elements. Okay, so it is called a domino. A single set, we call it as a domino. It is arranged in a pattern like you have a numerator and denominator, something like this. Either 0, 1 or ABC or any kind of set will be there. So each set is called a single domino. It has a numerator and a denominator. Okay, so our task here is to arrange this set in a format like we can mix and merge these set of dominoes, or sometimes we can exclude some of the dominoes, or sometimes we can repeat the dominoes too, and in such a way that finally after rearranging this dominoes, the strings that is formed by combining all the numerators should be equal to the string that is formed by the denominator. Okay, so I'll take one example. I'll show you how it is exactly working. So these two examples I'm going to show like how to find a solution for it. So first consider this domino, this set of dominoes. So I'm going to rearrange these set of dominoes such that it is going to have a solution. Solution in the sense like while combining all the numerator and combining all the denominator, it should be equal. Okay, so in case if I start with the last domino, if my starting input is 1, 0, 0, I cannot start with it, right? See, when I combine this numerator, it is 1, 0. In denominator, it starts with 0. Okay, as per our solution, like the numerator and denominator has to have a match. So we cannot start with this domino. And in case if I'm starting with the first domino, 1 by 1, 1, 1, your first element matches. And next, I want two ones to the top. But the problem is each domino, the remaining dominoes I have 1, 0, 1, 0. So only thing is I can again repeat these dominoes n number of times, but still you don't find the solution for it. So this we cannot start with this domino too. So we can start with this domino as 1, 0, triple 1, 1, 0. Okay, so that is your second domino. We are starting with it where 1, 1, 0, 0 matches. Okay, so now in the bottom, the next domino that I'm going to choose, in the bottom, I need all ones. So preferably, I'll take this first domino. It is all three ones. So this three ones and this three ones are matching. Now again on the top, I have a single one. So in the domino that I'm going to choose at the remaining portion, I should have bottom one here. So this things are matched. So for this one, in the bottom, I should need a 1. So I can either choose this domino or choose this domino. Okay, if I am choosing this first domino, like if I'm choosing the second domino, I'll just write for the second domino. So my problem will be like this. So I'll be choosing this domino. And when you are finding the matching part for this one is matching. And for this one, you don't have a match pair. Okay, you have a 0 here. So we cannot use this domino here. So the only possibility is to choose the first domino again. When I am choosing the first domino, your structure will look like this. So for this one is cancelled, and for this one is cancelled. Okay, so now I have a 1 at the bottom, one extra element. So I have to choose a domino that has 1 at the top. So all the dominoes have 1 at the top, but when I choose this third domino, that is 1, 0, 1, your pair completes. So for this one is cancelled. So this is 0. For the 0, the 0 is cancelled. Okay, so when the dominoes are arranged in a pattern, this is your solution. When the dominoes are arranged in a pattern such that 2, 1, 1, 3, if it is arranged in this pattern, then the string that is formed by combining the numerator on the top, we can call it as an x value. It is first step is 1, 0, 1, 1, 1 for this domino, and 1 here, and you have 1 here. Okay, and you have 1, 0 here. So this is your x, and y value is all the denominator. 1, 0 for the first set, and triple 1 for the next, triple 1 for the next domino, and 0. See, it is same. Okay, so this is called a post correspondence problem. A domino can be repeated any number of times, and sometimes we can exclude some of the domino too without including it into the solution. Okay, so for this set, you can make it as a try. I can either start with this domino 1, see TT matching. I cannot use start with the second domino, but here also HT matches. I can use this also starting domino. and I can use this also as starting domino. Okay, so take it as a work and try to find the solution for it. I'll just give you the list of solution. I'll give you one possible solution. It is like 1 2 1 3 3 2. So this is one possible. When the dominoes are arranged in this pattern, you can get a solution. So look into this place. So this one domino is repeated twice, two domino repeated twice, and three domino also repeated twice. Where fourth domino we haven't used it all. Okay, or I can even have this arrangement as can have this TT HH matches or some other possible match. Over here, if I start with domino 4, my fourth domino is TTT. Okay, so this T and this T is matching, and you have a top T. And when I have this domino 2, it is H and TH. See, for this T, T matches, and for this H, H matches. By combining the numerator, you have TTH, and the denominator, we have TTH. So it also matches. Okay, so this is post correspondence problem. And I'll just tell you that this is not the only way of arranging your dominoes. Like some of the places, they will use a different representation. Rather than arranging it in a box structure, they will be going with a list form too. Okay, so these dominoes can be put it in such a way that all your x numerator comes here, all your y denominator comes here. So first domino, you have 1 triple 1. 1 in the numerator, so this will be called as x1 and this will be called as y1. Okay, and for the second portion, it is 10111, the numerator port 10 here. So this is your x2 and this is your y2. And for the third, it is 100, x3 and y3. Okay, so for your convenience, you can take this either a list format or a domino format, but both are acceptable. Okay, I'm convenient with this domino representation. So I'll just go with this divisions kind of structure. Okay, I'll take one more example where you'll be having an looping structure too. Consider this set of dominoes. Now, let us take it as AB, ABB, BA, AA, and AB, BB. Okay, when you're finding, so this is your first domino, second and third. When you want to find a solution for this set, so I cannot start with second domino since the first digit here, first letter here is B and the bottom it is A. It is not matching. And for third also you don't have match. So only possibility is I have to start with my first domino as ABB. So here exactly AA matches, BB matches. In the bottom we have a B. So next I have to select a domino that has B at the top. So only possible domino that has B at the top is second domino. I write the second domino. I'll just write the solution steps too. This is first domino. This is second domino. So for this B matches. For this A matches. Now you have A. So when you have A, you have two possible combinations to be addressed. One is I can use this domino 1. When I am using domino 1, my solution will look like this. Okay, so for this A will be cancelled. For this B, you don't have a pair. Okay, I just want A at the top to use this domino, so I cannot use this domino. Okay, so only possibility over here is to use this third domino. When I am using third domino, I have AB, BB. So for this A cancel. For this B cancelled. Now I have B at the bottom. So I have to have choose a domino that has B at the top. So only possible domino is it is 2, it is BA and AA. Got it? For this B will be cancelled. For this A will be cancelled. Again, we are going into the same looping structure. I need a domino that has A at the top, a numerator. But when I choose the first domino, ABB, for this A can be cancelled. For this B, you don't have a pair here. So we cannot use it. Like the string formed by combining the numerator and the string formed by combining the denominator has to be same. Okay, so only way I'm going to choose it is like only possibility is choosing the third domino. It is AB and BB. For this A cancelled. For this B cancelled. So I need to choose a domino that has B at the numerator, and only possible domino that I B at the numerator is second domino. See, when you see the sequence, this 2 and 3 are entering into the loop. Okay, so for these kind of problems, when you put it into an automated system, it may enter into a looping structure. When it have a solution, it will report the solution and it will leave. But there is a possibility of this post correspondence problem entering into a looping structure without any halting to. So that is why we call this post correspondence problem as undecidable. Okay, to solve these kind of undecidable problem, there is no procedural way of showing that this post correspondence problem is undecidable. So one way is we can construct, like we already know that the problem of Turing machine is undecidable, right? For any language, when you want to construct a Turing machine, undecidability is when the input belongs to the language, whatever input that you are taking, if it belongs to the language, input will be accepted. Or if input doesn't belongs to the language, we are not sure about the prediction. Okay, either the Turing machine will halt or it doesn't halt. It will either reject it or sometimes enter into a looping criteria too. See, I'll just give you one example. Like when you have a Turing machine of the structure, when you want to construct a Turing machine of the structure, input is 10 in Q naught. If the input is 1 will remain as it is. We are moving right to Q1 state. Okay, in Q1, it goes here. In Q1, it treats the input as 0. If the input is 0, 0 will remain as it is. It moves left. So this is a Turing machine. For some of the input, very specifically when the input is given as 1, 0, what your Turing machine will do? It will enter into an infinite loop. Okay, so you may have other transitions too, but it is very specifically, it is input specific. Okay, you may have some other parts that is forthcoming over here and all. But in case, if for some of the specific input, your Turing machine may enter into the looping structure, but that is in, we cannot predict that. The reason is like you will be having an infinite possible inputs. We cannot check for all possible input whether the Turing machine is entering into is accepting or rejecting or entering into a looping structure and all. Okay, so this is called an unpredictability, undecidability. We cannot decide when your Turing machine going to accept, like when your Turing machine is going for a looping structure, and there are a lot of theorems to prove that Turing machine is undecidable. We have halting problem of Turing machine is undecidable. So all those things are already proven one. Okay, so we are going to use this relationship. We already know that Turing machine is undecidable, and we are going to use this as a reference for proving post correspondence problem is also undecidable. Okay, so we are going to take a Turing machine problem and convert that into a post correspondence problem. Like Turing machine problem will be like this, something in case of your transitions and functions. So we are going to convert these transition functions into some set of dominoes, and we are going to rearrange the dominoes such that we are able to find a solution. If your Turing machine goes to accepting state, then we have a possibility of arranging your dominoes for getting a solution, combining all your numerator, combining all your denominator, it has to be equal. Okay, so we are able to find a possible solution. Okay, but the problem is we cannot straight away make this conversion. We have to have a modified version of this post correspondence problem. And in this modified version of post correspondence problem, I'm just going to have an assumption that my starting domino is always a matching domino. Okay, so we'll be having plenty of dominoes, right? In the modified post correspondence problem, I'm going to start with the step that I'm going to have my first domino as a matching domino, and the remaining sets will be converted based on the Turing machine problem. Okay, so for today's session, I'm going to take one example problem, one scenario problem. I'll construct a Turing machine for it, and that Turing machine will be constructed to a modified PCP. And if I'll just show you how it is going for an acceptance, if the Turing machine goes to an accepting state, how your PCP, MPCP also has a solution for it. Okay, so let me show you that first. Okay, so this is the problem that I'm going to take. Construct a Turing machine to identify the employee ID of an institution. The ID is formed in such a way that it starts with a digit followed by a letter. Okay, so starting it has to be a digit followed by a letter, then it is followed by 0 or more letters or digit. Okay, and 1, 2, 3 are the only allowed digit. and that can be included, and R is the only letter that can be allowed. So your input is made up of, this is very important, your input is exactly made up of either 1, 2, 3 or R. Okay, so when it is starts with, like, the starting element is a digit, so it will be either 1 or 2 or 3, and the next element is a letter, so it has to be R. So if this criteria satisfy, we can accept your input. So we are going to construct a Turing machine to identify whether it is a valid ID or not, and we are going to find a modified version of this PCP. Convert this Turing machine into a PCP problem, modified PCP problem, and in the modified PCP, we are going to take this as an input and we are going to verify it has a solution or not. Got it? So I'll do step by step. Listen carefully. So here your digit and your what is a letter is defined. So this is your input function. I can define my tau also. Tau is the element that can be written on the tape. So the allowed digits are 1, 2, 3, and the letter is R, or we can have a blank symbol. Just have this representation. This shows that these are all the only possible element that can appear in a tape. Okay, we don't want to universally go for all possible combination of 1 to 9 digit and A to Z. So that will be really complicated. So I don't want to go ahead like that. So I can stop that in my tape. The only possible element that can occupy in my tape is either 1 or 2 or 3. Only 3 digits. R is the only letter, and the remaining space is occupied by the blank symbol. Okay, so with this consideration, I'm going to start my Turing machine. I'm going to draw the transition diagram for it. So the transition diagram here is very simple. So in my Q naught, the first element should be a digit. Okay, so I'm going to scan. Like whenever you start your Turing machine, it works like this here. The input will be returned in the tape. Each cell is capable of storing one element at a time, and your read-write head focuses on the first element in the starting stage. Okay, and while scanning the first element, our identifier should start with the digit. So first element should be a digit. If it is a digit like either 1 or 2 or 3, okay, if the input is 1 or 2 or 3, we can go for the next step. Okay, so if it is 1, 1 will remain as it is, move right. If it is 2, 2 will remain as it is, move right. 3, 3 will remain as it is, move one step ahead to Q1 state. So first element is scanned. If it is a digit, it is pakka. I'm going to the next step. In my next step, it should be followed by a letter. Okay, all your digit followed by a letter, and the letter that is allowed is R. So if the second element is R, you are going for this acceptance criteria. It is followed by 0 or more letter or digit, which doesn't matter. Okay, since in my tape, only letter and digits are allowed to occupy. Okay, so I'm not bothered about the remaining element. So if my first element is a digit and the second element is the letter R, I'm going for this acceptance state. Q accepting state. So this R will remain as it is, and we are making a left side move. So while going for your acceptance state, either move left or right, it doesn't matter. But there is a step for modified PCP construction where this left side move has a, like for left side move, we have a specific way of representation. So that is why I made this left side move. You can either make it as right side move too. It is up to you. Okay, so we have constructed your Turing machine. So when the input given is a valid identifier, your Turing machine will goes to accepting state. First step is done. Second step is I have to construct a modified post correspondence problem for it. I have to modify this PCP, so this Turing machine into a PCP problem. Okay, and listen carefully dear, there are 7 steps to follow this MPCP function. So I'll just combine that 7 step for our example too. Okay, rather than discussing that 7 steps separately and doing it for our problem separately, I'll take it all together. Okay, so first step is, listen carefully, the steps are very, very important, this conversion. So first step here is to start with, like whenever you start your Turing machine will be started like this. Okay, the input tape is splitted into cells, and you have a read-write head focusing on the first element. This is a standard structure, and the input is written in the tape from left to right. Okay, and we commonly use this W representation for input. So the first step is to include this domino. As in the modified PCP, I told you now we are going to have a matching domino as the first domino. Okay, so you have hash hash matched. And what will be your instantaneous description for it here? What is your instantaneous description? See, when I have a tape structure like this, return 1, 0, 1, 1. And if my read write head focus on here with QX, how can I give an instantaneous description for it? I have to write the content in the tape. 1 will remain as it is, 0 will remain as it is. And wherever you have your read write head, you have to write your state here. Okay, instantaneous description is very important. We'll be using that in step 1, step 2, and step 3. You should know what is instantaneous description. Okay, so ID description is in a single line, we are making this representation as a whole. Okay, so first the element in the tape will be written as it is 1, 0, and wherever you have your read write head, to the prefix of it, you have to add this state. Okay, so this is the place where your read write head focus on. So before that, I'm going to write it as QX 1, 1. So this is called ID description. This is your tape representation and this is your ID description. And here, how can you write it? Your input is written in the tape. So W is your input and that is written in the tape from left to right. And Q naught focus on the first element. When you want to write the instantaneous description for it, it is Q naught W. So W will be your input and the place where your read write head focus on, you have to add your Q naught state to the prefix of it. Okay. So first instant will be like this. This is your first domino. Okay, so Q naught is a starting state followed by your input. This is the first instant of your tape structure. And when you are doing it for a specific input, so I'll just combine it with the input structure too. So in the given input, in the given problem, see, you check this step 3, check whether the string, so this is the input string that is needed to be checked. Your W is 2R13 has a solution or acceptance using MPCP. So we have to verify whether this 2R13 has a possible solution or not. Okay, so this is my input. So my first domino will be hash Q naught is your starting state that will remain as it is, and this is your input. So you have to write 2R13 hash. So this is my first domino. This is the first modification. We are going to do it in a PCP problem. Okay, step 1 is done. Step 2. Step 2 is for all transition of right move. Okay, so wherever you have a transition with the right side move, after making this transition, it moves to right, right? So for those kind of transitions, how we are going to create a domino? Look at the transition very carefully dear. Like we have all your right side move here. We have 3 places where you have your right side move, and each step it is like this. Your input is either 1. I'm just taking this transition here. Transition of Q naught, first transition. Okay, Q naught, when the input is 1. So this is before transition. We make a move to Q1 state. 1 remain as it is, and we are making a right side move. Okay, so Q naught, by reading a 1 in the tape, we are making a right side move to Q1 state. Okay, so how can you write a instantaneous description for it? So for this, your read write head focus on the place before 1. Okay, so the instant for this is Q naught 1. Okay, so this is before transition, we have Q naught 1. And after transition, 1 remain as it is in the tape and your read write head focus on the next cell. And before that, you are able to write this Q1. So this is the instantaneous description for after transition. Okay, so 1 will remain as it is and your read write head focus exactly on 1. So it is Q naught 1. Like instantaneous description is wherever your read write head focus on, to the prefix of it, you have to add your state. So this is Q naught 1. And in this place, after transition, 1 will remain as it is, but your read write head moves 1 step ahead. But when you are writing the instantaneous description, 1 will be followed by this Q1. Okay, so with this said, we are going to form a domino. Okay, so where the numerator carries the place before transition and denominator carries the place after transition. Okay, so before transition, this is the place where Q01 will be there in the tape. And after transition, we have one Q1. Okay, Q0 is transisted to Q1. So this is for the first input that I have taken, 1, comma 2. For the next input, instead of 1 in the tape, you have 2. But the remaining procedure is same, right? Q naught on reading the input as 2. Q naught on reading the input as 2. 2 will remain as it is in the tape. So 2 will remain as it is in this tape. We are making one step left. So all this 1 is converted to 2. So this is before transition and this is after transition. See, all the transitions are same. If you are reading 1, 1 will remain as it is in the tape. We are moving right. If you are reading 2, 2 will remain as it is in the tape. Moving right. 3, 3 will remain as it is. We are moving right. And the transition is moved from Q0 to Q1. Okay, so the next domino created will be Q0 2 by 2 Q1. And for the third transition, it is same, right? Q0 3 implies Q1 3R. So in your tape, you will be having a 3 and Q0 here. Q0 on reading the input as 3, 3 will remain as it is. We are making one right side move to Q1 state. So the instantaneous description for it is Q0 3 and the instantaneous description for this is 3Q1. So the domino that is formed over here will be Q0 3 and 3Q1. Okay, so this is your step 2. Step 2 is for all your right side move. And much concentration is needed for step 3. Okay, step 3 is a place for your left side move. When you are going for your left side move, a single caution is needed. Okay, so understand how you're going to do it carefully. So this is your step 2. Step 3 is transition for all left move. Okay, so you have only one possible left side move, that is from Q1 to Q accepting state. So you will have the transition like this. Transition of Q1 when the input is R. We are going for Q accepting state. R will remain as it is and we are making a left side move. Okay, so how you are going to draw a tape structure for it? You have a R here and Q0 here. Sorry, Q1 here. After transition, this R will remain as it is. We are making one left side move to Q accepting state. Okay, so now listen carefully. When I want to do a instantaneous description for this place, my read rate head focus on the blank symbol. Okay, not a blank symbol. It is one tape element, like some tape element should be there. Okay, the element that are allowed in this tape for this Turing machine is either 1 or 2 or 3 or R or the blank symbol. So these are all the only allowed elements that can be written in the tape. So any one of the tape element will be present in this place. We are not sure which tape element it is. And when you want to write a transition, an instantaneous description for this, your QA has to be added here. So after transition, your transition will look like this. QA tape element followed by R. And before transition, it is tape element and your read head focus on it. So to the prefix of it, we have to add the state. It is Q1 R. So this is before transition and this is after transition. So here your tape element comes in between. We cannot ignore this case. Okay, so for all possible tape elements, you have to rewrite this domino. Okay, so tape element might be either 1 or 2 or 3 or R or blank. So for all possible tape elements, you have to rewrite this transition by including the tape element in this place. Okay, so this is very specific for left side move. The reason is when you are making a left side move, your tape element, some element in the tape comes in between the domino. Okay, we cannot directly ignore this case. Okay, so when you are writing for all possible tape element, the transition will look like this. If my tape element is 1, I have to rewrite this transition as 1 Q1R QA1R. So wherever I have tape structure, I have entered the value as 1. And if my tape element is 2, the domino formed will be 2 Q1R and QA 2R. When my tape element is 3, 3Q1 R followed by QA 3R. And when my tape element is R, Q1R, QA RR. And when my tape element is blank symbol, it is blank Q1R, okay, QA blank R. So these are all the possible tape element that can come into this place. So for all possible element, we have written a transition dominoes representation for left side move. So the caution is made whenever we are making a left side move. For right side move, it doesn't matter, but for left side move, you have to carefully make this transition. Got it? Now coming to the remaining steps. Remaining steps are very simple. Only these three steps are a bit complicated, and that too with this left side move step, it is a bit complicated. Okay. So now we are in step 3, and step 4 is step 4 for all the tape symbol. For all your tape symbol, we are going to write a matching domino. Your tape symbols are this. So when I have 1 in the tape, 1 1, 2 2, 3 3, 4 4, and then so not 4. The digits allowed are 1 2 3, and you have R R, and then you have blank blank. Okay, so these are all the possible tape elements, and this is the matching domino for each tape element. Very simple. And the step 5 is very important. Step 5 is a conception phase. Once after reaching your Q acceptance state and all possible tape elements, you're going to write the transition as if. The format is, can use this as a format. Tape QA can be written as QA. This is one domino. QA tape element as QA. Okay, this is your conception phase. Okay, so this tape element might be, I'm sorry, this is your tape symbol, right? So this tape element might be anything of 1 or 2 or 3 RR blank. For all possible combination, you have to write the matching domino here. Okay, so it is 1 QA can be written as QA, or QA1 can be written as QA. This is conception phase here. You'll know about it when you are solving a problem. 2 QA can be written as QA, and QA2 can be written as QA. 3 QA can be written as QA, and QA3 can be written as QA. Okay, and what all the remaining dominoes, like tape symbol, you have R and blank. Write it for RQA as QA, and QAR as QA, and blank QA as QA, and QA blank as QA. This is your step 5. And finally, we have step 6 and 7. That is easy. That is going to be common for all. So step 6 is include this domino, hash hash, or hash blank hash. This is your step 6 and step 7. For all the problem, your step 6 and step 7 is same. Okay, so there is no modification. Q except hash hash, denominator is hash. Got it? So the entire Turing machine, these are all the 7 steps that you want to make. Like this is your Turing machine problem, and this is your modified PCP. We have converted the Turing machine problem into some set of dominoes like this. Okay, so next step is to simulate, like to check whether your Turing machine is accepting or not. We are going to combine that dominoes and try to find a solution for it. So that is your ultimate aim, right? Our goal is to use the domino for finding whether to check whether we are able to find a solution or not. Okay, so let's start this. So first domino is, as I said, we are going to always start with the matching domino. So first step, I'm going to start with the first domino, that is this one. Okay, Okay, it is hash hash q naught 2r13. This is my input hash. Okay, so this is my matching domino. So for this hash matches. Now for q naught and 2, we have to find a domino that has q naught 2 at the numerator. We should have a matching dominoes, right? See, this is the domino that has q naught 2 at the numerator. So take this domino, q naught 2, and the domino is 2q1. So this q naught matches, and this 2 matches. Okay, for all the remaining tape elements, you take this matching dominoes. Okay, so you have the next element as R. Take this RR domino. So this R and this R matches, and next element is 1. Take 1 1 domino. So for this one matches, and next domino needed is 3 3 3 and 3. So for this 3 is cancelled, and next you have hash. Use step 6. We have hash domino here, right? Included here. Hash. Okay, so this hash and this hash matches. So here in the first, all the dominoes of the first, all the elements of the first domino is having a matching element in the remaining pairs. Okay, so this is your first step. After your first step, what is the resultant thing? All your numerators are cancelled out. So you don't have anything in the numerator. In the denominator, it forms a new phase. That is 2q1r13 hash. Okay, so this is there in the denominator. Now we have to have this in the top. 2q1r should be there in the top, and you have to take a domino that has the same structure. See here, 2q1r is here. Okay, so you can use that domino here, 2q1r, and the bottom of that is you have qa2r. We have to arrange this domino such that your numerator and denominator matches perfectly. So this 2 cancelled, this q1 cancelled, and this r cancelled. Okay, so later you have 1 in the tape. Take the matching domino as 1 1. So this one will be cancelled. Next you have 3. Take the domino as 3 3, matching domino. This 3 cancelled, and hash, for the hash you cancel this, use this hash domino. For this hash will be cancelled. Okay, so now we are entering into the Q accepting state. Now I'll just write it here, the remaining part. So in this place, all your numerators are cancelled out, and in your denominator we have qa2r 13 hash. Okay, so at this place I need a domino with 2 qa2. See, in your step 5, it is your conception phase, I told you, right? All your dominoes are taken, like you have this 2qa. After reaching your acceptance state, we are just going to follow this things, the dominoes that are used in step 5. Okay, in the, sorry, not this domino, it is qa2. This domino that has qa2 at the top, and the bottom we have qa alone. So this qa cancel, this 2 cancel. Okay, so remaining things you can directly merge it up with the tape symbol, matching dominoes. Next you have R. For this R, use RR domino. And next you have 1. For 1, use this 1 1 domino. And next you have 3, use 3 3 domino. And next you have hash, use hash domino. Okay, so this in all matches. So next step is all your numerator are cancelled. In the denominator, we have the new formed domino as QAR13 hash. Okay, so now you have QAR. So for QAR, you have to use this domino, QAR. Okay, so in the numerator, we want to use a domino with QAR. So I'm just taking that domino. It is QAR, and the bottom it is Q accepting state. So this QA matches, and this R matches. Now I have 1 in the bottom, use 1 1, 3 3 matching dominoes, and you have hash function. Okay, so this one matches, this 3 this 3 matches, and this hash matches. Okay. Finally, the left out portion here is all your numerator are cancelled. In the denominator, we have QA13 hash. So I'm going to use this domino as QA1. It is there in step 1. You can use that, verify that. QA. So this QA matches 1 and 1 matches. And the remaining tape elements, like the matching domino needed, is 3, 3 and hash hash. Okay. So this 3 matches, this hash matches. All your numerators are cancelled. Now in the denominator, I have QA3 hash. Okay. In your step 5, take the domino with QA3. You can verify here, it is QA. So this QA matches, this 3 and this 3 matches. And finally, you have hash domino to be matched. Okay, so this hash and this hash is matching. Okay, and the last step is, now you have in the denominator, you have QA hash. All your numerators are cancelled. In the denominator, we have QA hash as the pending one. So this is the final structure. You have QA hash in the denominator. You have to find the matching domino. That is there in your 7th step. Okay, so when you include that, it is QA hash. At the bottom, we have a hash. Okay, so this QA and this QA cancel, this hash and this hash cancel, this hash and this hash cancelled. So entirely after transition, after combining all those dominoes, the string that is formed by combining all your numerator and the string formed by combining all the denominator are same. So that is your PCP problem, right? So we have taken a Turing machine problem, formed set of dominoes, and if my Turing machine goes to accepting state, my domino has a solution for it. So with that, we can say that if my Turing machine has an acceptance criteria, my PCP also has an acceptance criteria. And sometimes if my Turing machine enter into a looping criteria, my PCP also has a possibility of entering into a looping criteria. So we know that Turing machine is already undecidable problem. So with that, we can give a justification that this PCP problem is also undecidable. We are able to convert this Turing machine problem into PCP, and since Turing machine is already undecidable, this PCP will also be an undecidable problem. So that is the final justification we want to give over here. Okay. So now I'll just come back to the question. See, construct a Turing machine, constructed. Modified version of Turing machine PCP, done. And finally, we have checked whether this is accepting or not using your MPCP instant. That is also done. Okay, so this is how you have to approach for any scenario-based question used as in this post correspondence problem. Okay, thank you so much, dear.